A communications satellite is an artificial satellite that relays and amplifies radio telecommunications signals via a transponder. It creates a communication channel between a source transmitter and a receiver at different locations on Earth. Communications satellites are used for television, telephone, radio, internet, and military applications. There are over 2,000 communications satellites in Earth's orbit, used by both private and government organizations. Wireless communication uses electromagnetic waves to carry signals. These waves require line of sight, and are thus obstructed by the curvature of the Earth. The electromagnetic signals that communication satellites work with have a large spectrum of wavelengths and frequencies. To keep these waves from interfering with one another, international organizations have certain rules and regulations describing which wavelength a certain company or group can use. By separating out wavelengths, communication satellites will have minimal interference and be able to communicate effectively. There are two major classes of communications satellites, passive and active. Passive satellites only reflect the signal coming from the source toward the direction of the receiver. With passive satellites, the reflected signal is not amplified at the satellite, and only a very small amount of the transmitted energy reflects toward the receiver. Since the satellite is so far above Earth, the radio signal is attenuated on its long journey due to free space path loss, so the signal received on Earth is very weak. Active satellites, on the other hand, amplify the received signal before retransmitting it to the receiver on the ground. Passive satellites were the first communications satellites, but are little used now. History. Today, satellite communications can trace their origins all the way back to February 1945 and Arthur C. Clarke's letter to the editor of Wireless World magazine. Clarke further fleshed out this theory in a paper titled Extraterrestrial Relays: Can Rocket Stations Give Worldwide Radio Coverage?, published in Wireless World in October 1945. Decades later, a project named Communication Moon Relay was a telecommunication project carried out by the United States Navy. Its objective was to develop a secure and reliable method of wireless communication by using the Moon as a natural communications satellite. The first artificial Earth satellite was Sputnik 1. Put into orbit by the Soviet Union on October 4, 1957, it was equipped with an onboard radio transmitter that worked on two frequencies, 20.005 and 40.002 MHz. Sputnik 1 was launched as a step in the exploration of space and rocket development. While incredibly important, it was not placed in orbit for the purpose of sending data from one point on Earth to another, and it was the first artificial satellite in the steps leading to today's satellite communications. The first artificial satellite used solely to further advances in global communications was a balloon named Echo 1. Echo 1 was the world's first artificial communications satellite capable of relaying signals to other points on Earth. It soared 1,600 kilometers above the planet after its August 12, 1960 launch, yet relied on humanity's oldest flight technology, ballooning. Launched by NASA, Echo 1 was a giant metallic balloon 30 meters across. The world's first inflatable satellite, or Sataloon, as they were informally known, helped lay the foundation of today's satellite communications. The idea behind a communications satellite is simple. Send data up into space and beam it back down to another spot on the globe. Echo 1 accomplished this by essentially serving as an enormous mirror, 10 stories tall, that could be used to reflect communications signals. The first American satellite to relay communications was Project SCORE in 1958, which used a tape recorder to store and forward voice messages. It was used to send a Christmas greeting to the world from U.S. President Dwight D. Eisenhower. NASA launched the Echo satellite in 1960. The 30-meter aluminized PET film balloon served as a passive reflector for radio communications. Courier 1B, built by Philco, also launched in 1960, was the world's first active repeater satellite. Telstar was the second active, direct relay communications satellite, belonging to AT&T as part of a multinational agreement between AT&T, Bell Telephone Laboratories, NASA, the British General Post Office, and the French National PTT to develop satellite communications. It was launched by NASA from Cape Canaveral on July 10, 1962, the first privately sponsored space launch. Relay 1 was launched on December 13, 1962, and became the first satellite to broadcast across the Pacific on November 22, 1963. An immediate antecedent of the geostationary satellites was Hughes' Syncom 2, launched on July 26, 1963. Syncom 2 was the first communications satellite in a geosynchronous orbit. It revolved around the Earth once per day at constant speed, but because it still had north-south motion, special equipment was needed to track it. Its successor, Syncom 3, was the first geostationary communications satellite. Syncom 3 obtained a geosynchronous orbit, without a north-south motion, making it appear from the ground as a stationary object in the sky. Satellite orbits. Communications satellites usually have one of three primary types of orbit, while other orbital classifications are used to further specify orbital details. Geostationary satellites have a geostationary orbit, which is 35,786 kilometers from Earth's surface. This orbit has the special characteristic that the apparent position of the satellite in the sky when viewed by a ground observer does not change. The satellite appears to stand still in the sky. This is because the satellite's orbital period is the same as the rotation rate of the Earth. The advantage of this orbit is that ground antennas do not have to track the satellite across the sky. They can be fixed to point at the location in the sky the satellite appears. Medium Earth orbit satellites are closer to Earth. Orbital altitudes range from 2,000 to 35,786 kilometers above Earth. The region below medium orbits is referred to as low Earth orbit, and is about 160 to 2,000 kilometers above Earth. As satellites in MEO and LEO orbit the Earth faster, they do not remain visible in the sky to a fixed point on Earth continually like a geostationary satellite, but appear to a ground observer to cross the sky and set when they go behind the Earth. Therefore, to provide continuous communications capability with these lower orbits requires a larger number of satellites. So one will always be in the sky for transmission of communication signals. However, due to their relatively small distance to the Earth, their signals are stronger. Low Earth orbiting satellites say low Earth orbit typically is a circular orbit about 160 to 2,000 kilometers above the Earth's surface and, correspondingly, a period of about 90 minutes. Because of their low altitude, these satellites are only visible from within a radius of roughly 1,000 kilometers from the sub-satellite point. In addition, satellites in low Earth orbit change their position relative to the ground position quickly. So even for local applications, a large number of satellites are needed if the mission requires uninterrupted connectivity. Low Earth orbiting satellites are less expensive to launch into orbit than geostationary satellites and, due to proximity to the ground, do not require as high signal strength. Thus there is a trade-off between the number of satellites and their cost. In addition, there are important differences in the onboard and ground equipment needed to support the two types of missions. Satellite constellation. A group of satellites working in concert is known as a satellite constellation. Two such constellations, intended to provide satellite phone services, primarily to remote areas, are the Iridium and Global Star systems. The Iridium system has 66 satellites. It is also possible to offer discontinuous coverage using a low Earth orbit satellite capable of storing data or seed while passing over one part of Earth and transmitting it later while passing over another part. This will be the case with the Cascade system of Canada's Cassiope communications satellite. Another system using this store and forward method is Orbit.com. Medium Earth Orbit (MEO) is a satellite in orbit somewhere between 2,000 and 35,786 kilometers above the Earth's surface. MEO satellites are similar to LEO satellites in functionality. MEO satellites are visible for much longer periods of time than LEO satellites, usually between 2 to 8 hours. MEO satellites have a larger coverage area than LEO satellites. A MEO satellite's longer duration of visibility and wider footprint means fewer satellites are needed in a MEO network than a LEO network. One disadvantage is that a MEO satellite's distance gives it a longer time delay and weaker signal than a LEO satellite. Although these limitations are not as severe as those of a geosatellite. Like LEOs, these satellites don't maintain a stationary distance from the Earth. This is in contrast to the geostationary orbit, where satellites are always approximately 35,786 kilometers from the Earth. Typically, the orbit of a medium Earth orbit satellite is about 16,000 kilometers above Earth. In various patterns, these satellites make the trip around Earth in anywhere from 2 to 12 hours, which provides better coverage to wider areas than that provided by LEOs. Example: in 1962, the first communications satellite, Telstar, was launched. It was a medium Earth orbit satellite designed to help facilitate high-speed telephone signals. But scientists soon learned what some of the problematic aspects were of a single MEO in space. It only provided transatlantic telephone signals for 20 minutes of each approximately 2.5 hours orbit. It was apparent that multiple MEOs needed to be used in order to provide continuous coverage. Geostationary orbits to an observer on the Earth. A satellite in a geostationary orbit appears motionless, in a fixed position in the sky. This is because it revolves around the Earth at the Earth's own angular velocity. A geostationary orbit is useful for communications because ground antennas can be aimed at the satellite without their having to track the satellite's motion. This is relatively inexpensive. In applications that require a large number of ground antennas, such as direct TV distribution, the savings in ground equipment can more than outweigh the cost and complexity of placing a satellite into orbit. The concept of the geostationary communications satellite was first proposed by Arthur C. Clarke, building on work by Konstantin Tsiolkovsky and on the 1929 work by Hermann Potocnik. Das Problem der Befahrung des Weltraums, der Raketenmotor. In October 1945, Clarke published an article titled Extraterrestrial Relays in the British magazine Wireless World. The article described the fundamentals behind the deployment of artificial satellites in geostationary orbits for the purpose of relaying radio signals. Thus, Arthur C. Clarke is often quoted as being the inventor of the communications satellite and the term Clarke belt employed as a description of the orbit. Examples: the first geostationary satellite was Syncom 3, launched on August 19, 1964, and are used for communication across the Pacific, starting with television coverage of the 1964 Summer Olympics. Shortly after Syncom 3, Intelsat I, aka Early Bird, was launched on April 6, 1965 and placed in orbit at 28 degrees west longitude. It was the first geostationary satellite for telecommunications over the Atlantic Ocean. On November 9, 1972, Canada's first geostationary satellite serving the continent, Anik 1, was launched by Telesat Canada, with the United States following suit with the launch of Westar 1 by Western Union on April 13, 1974. On May 30, 1974, the first geostationary communications satellite in the world to be three-axis stabilized was launched. The experimental satellite -6 Austrian shillings built for NASA. After the launches of the Telstar through Westar 1 satellites, RCA Americom launched Satcom 1 in 1975. It was Satcom-1 that was instrumental in helping early cable TV channels such as WTBS, HBO, CBN and the Weather Channel become successful, because these channels distributed their programming to all of the local cable TV headends using the satellite. Additionally, it was the first satellite used by broadcast television networks in the United States, like ABC, NBC, and CBS, to distribute programming to their local affiliate stations. Satcom-1 was widely used because it had twice the communications capacity of the competing Westar-1 in America, resulting in lower transponder usage costs. Satellites in later decades tended to have even higher transponder numbers. By 2000, Hughes Space and Communications had built nearly 40% of the more than 100 satellites in service worldwide. Other major satellite manufacturers include Space Systems, Loral, Orbital Sciences Corporation with the Starbus series, Molniya satellites. Geostationary satellites must operate above the equator and therefore appear lower on the horizon as the receiver gets the farther from the equator. This will cause problems for extreme northerly latitudes, affecting connectivity and causing multipath. Thus, for areas close to the North Pole, a geostationary satellite may appear below the horizon. Therefore, Molniya orbit satellites have been launched, mainly in Russia, to alleviate this problem. Molniya orbits can be an appealing alternative in such cases. The Molniya orbit is highly inclined, guaranteeing good elevation over selected positions during the northern portion of the orbit. The Molniya orbit is designed so that the satellite spends the great majority of its time over the far northern latitudes, during which its ground footprint moves only slightly. Its period is 1/2 day, so that the satellite is available for operation over the targeted region for 6 to 9 hours every second revolution. In this way, a constellation of 3 Molniya satellites can provide uninterrupted coverage. The first satellite of the Molniya series was launched on April 23, 1965 and was used for experimental transmission of TV signals from the Moscow uplink station to downlink stations located in Siberia and the Russian Far East, in Norilsk, Khabarovsk, Magadan and Vladivostok. In November 1967, Soviet engineers created a unique system of national TV network of satellite television, called Orbiter, that was based on Molniya satellites. Polar Orbit in the United States. The National Polar Orbiting Operational Environmental Satellite System was established in 1994 to consolidate the polar satellite operations of NASA. NOAA-NPOESS manages a number of location company. METSAT stands for Meteorological Satellite. EUMETSAT stands for the European Organization for the Exploration of the METSAT Program. METOP stands for Meteorological Operations. These orbits are sun-synchronous, meaning that they cross the equator at the same local time each day. For example, the satellites in the NPOESS orbit will cross the equator, going from south to north, at times 1:30 p.m., 5:30 p.m., and 9:30 p.m. Structure. Communications satellites are usually composed of the following subsystems. Communication payload, normally composed of transponders, antennas, and switching systems. Engines used to bring the satellite to its desired orbit. Station keeping, tracking and stabilization subsystem used to keep the satellite in the right orbit with its antennas pointed in the right direction, and its power system pointed towards the sun. Power subsystem, used to power the satellite systems, normally composed of solar cells, and batteries that maintain power during solar eclipse. Command and control subsystem, which maintains communications with ground control stations. The ground control Earth stations monitor the satellite performance and control its functionality during various phases of its life cycle. The bandwidth available from a satellite depends upon the number of transponders provided by the satellite. Each service requires a different amount of bandwidth for transmission. This is typically known as link budgeting, and a network simulator can be used to arrive at the exact value. Frequency allocation for satellite systems. Allocating frequencies to satellite services is a complicated process which requires international coordination and planning. This is carried out under the auspices of the International Telecommunication Union. To facilitate frequency planning, the world is divided into 3 regions. Region 1, Europe, Africa, what was formerly the Soviet Union, and Mongolia. Region 2, North and South America and Greenland. Region 3, Asia, Australia, and the Southwest Pacific. Within these regions, frequency bands are allocated to various satellite services. Although a given service may be allocated different frequency bands in different regions, some of the services provided by satellites are fixed satellite service, broadcasting satellite service, mobile satellite service, radio navigation satellite service, meteorological satellite service, amateur satellite service.